Now let's see what happens at the swing limits. First of all, I'll write down the quiescent quantities here, or the operating point values. So this is 3 volts and that is 3 volts, and the operating point voltage here is 0. When Vi is 0, this is at 0 volts, and the output is also at 0 volts. Okay, this capacitor will be charged to 3 volts at the operating point. Now when a signal Vi is applied, obviously this becomes 3 volts plus Vi. Okay. Now if you look at the point at which the transistor enters triode region, that is when Vi equals 0.17 volts, this becomes 3 volts plus 0.17 volts, or 3.17 volts. Now the output is, when Vi is 0.17 volts, the output here is 0.17 times minus 4.8, which is the gain, which is minus 0.83 volts. Okay. And here at the drain, the voltage will be 3 volts minus 0.83. The incremental voltage here and there will be the same, because C2 acts as a short for signal frequencies. In other words, C2 just holds 3 volts. Okay. So this voltage here would be 3 volts minus 0.83 volts equals 2.17 volts. Okay. Now you see what has happened. The gate voltage is increased to 3.17 volts. The drain voltage has fallen to 2.17, exactly 1 Vt below the gate. So clearly now this is at the edge of triode region. Any further increase in the input voltage, this will go down further and it will enter the triode region. So this is the limit. Okay. At the input, when the input is plus 0.17, it will reach the triode region. If you want it in terms of the output, when the output is minus 0.83 volts, it would have entered the triode region. Okay. Now let's look at the cutoff limit. Let me again write down the values. The quiescent voltage here is 3 volts, there it's 3 volts, across C2 it is 3 volts, at the output it is 0, and at the input also it is 0 in the operating point or quiescent condition. Okay. We evaluated that the cutoff limit occurs when Vi is minus 1 volts. Okay. The quiescent current here is of course 200 microamperes. Okay. Now when the input is minus 1, the incremental VGS is minus 1. Volts. So the incremental current would be Gm times VGS, which is 200 microsiemens times minus 1 volts. Okay. So the total drain current is 200 microamperes minus 200 microsiemens times 1 volt, which of course is 0. Okay. So at cutoff, what happens is the transistor is cut off, its drain current is 0, and this is as good as an open circuit. And this resistor, of course, we consider it an open circuit because it's so large. It's not exactly an open circuit, but we have chosen its value to be so high that no current flows through it. Okay. So the condition at cutoff is that there is no current here and there is no current there. So essentially we have just this circuit. So here it is open circuited, and we have C2 and we have RL, which is 40 kilo ohms, 60 kilo ohms and 15 volts. Okay. And C2, of course, it holds 3 volts, its operating point value, because the incremental voltage across C2 is 0. Okay. When we say C2 is a short circuit for signals, it means that its incremental voltage is 0 in presence of the signal, which is at some frequency omega. So across C2 you have a constant 3 volts. So actually you can evaluate the cutoff limit also in this way. Okay. In this case you have 3 volts across this and 15 volts applied across the total. So the total current that is flowing this way, let me call that IL prime. So IL prime would be 15 volts minus 3 volts divided by the total resistance, which is 100 kilo ohms. Okay. Which is essentially 120 microamperes. Now when IL prime is 120 microamperes, you can easily calculate that you have 7.2 volts across this and 4.8 volts across the load. Now let's go back to our limit in terms of the output. What did we say was the limit? V0 must be less than 4.8 volts. Okay. Of course, we should get exactly the same value because it's the same condition we are evaluating. We just assume that the capacitor holds a constant voltage and this is an open circuit because the transistor is cut off. So obviously you get the same limit. So the output is 4.8 volts when the transistor just cuts off. And also interesting is what this value is. That value is 15 minus 7.2, which is 7.8 volts. And another way to calculate the same thing is to add the quiescent drain voltage, which is 3 volts, and the incremental drain voltage, which is minus GM RD parallel RL times minus 1 volt. Okay, in other words, 3 volts plus 4.8 volts, which becomes 7.8. Okay, so when the transistor just cuts off, this point reaches 7.8 volts. Okay, now this is actually quite important to remember. Occasionally students make the mistake of assuming that because the transistor is cut off and there is no current here, there is no current in the 60 kilo ohm resistor as well, so that means that this would have reached VDD. Okay, but that's not correct. What happens is, as this voltage rises, the current in this reduces and the current in this increases. Okay, so when it is 3 volts, there is 200 microamperes here and 200 microamperes there and no current going that way. That's the quiescent condition. As this voltage goes above 3 volts, obviously the voltage across the resistor reduces and the current here reduces. Okay, and this voltage also increases, so the current here increases. Okay, so a part of this current also goes that way and the drain current reduces even further. And cutoff is the point where all of this current is flowing into that, and that current is not zero unless this load resistance is an open circuit. It is infinitely large. Okay, so if this 40 kilo ohm was not there, if it was an open circuit, then when the transistor cuts off, this voltage reaches 12 volts. But because we have a load resistance, this does not reach VDD. Okay, this is an important thing to remember. This also shows you that all our calculations are consistent with each other. We add the increment to the operating point, or we can imagine that at cutoff there is no current here and the current flows that way. Okay, so this is a summary of swing limit calculation for a different topology, that is common source amplifier with drain feedback. The swing limits depend on the exact biasing circuit and quiescent values of VDS and VGS and so on. Okay, now with this illustration you should be able to calculate the swing limit for any circuit. Okay, the procedure is always exactly the same. You find the total VDS, total VGS, or total VD and total VG, whichever is more convenient for your comparison, and also the total drain current ID. How do you obtain the total quantities? You add the operating point quantities to incremental quantities. The incremental quantities are obtained from small signal incremental analysis, which is linear. Okay, and then once you have all of these things, you apply the limits. VDS must be more than VGS minus VT and ID total must be more than 0, and you get the two limits for the signal. Okay, so this is the summary. Evaluate the total quantities and the total quantities are the sum of the operating point quantities and incremental quantities, and this part comes from small signal linear equivalent circuit, and then apply triode and cutoff limits, and typically you evaluate this in terms of either the input voltage or the output voltage, whichever you wish to have. Okay. And also, by doing circuit analysis, once you evaluate the limits, you should be able to say what happens to any other voltage or current in the circuit at those limits. Okay, because that again comes from the usual incremental analysis. Now later you will run into circuits with multiple transistors. Okay. Now what do? You again do exactly the same thing, but you calculate the triode or cutoff limit for one transistor at a time. Okay. So now let's say because of some transistor M1, Vi happens to be within these limits. Let's say the upper limit is half a volt and the lower limit is minus 1.5 volts. And because of M2, the upper limit happens to be 1 volt and the lower limit happens to be minus 0.75 volts. So you do it for every transistor. There could be 100 transistors, you do it for every one of them. And then what you do? You take the worst case, that is lowest of the upper limits and highest of the lower limits. And in this particular case, obviously, Vi should be limited to 0.5 volts because otherwise M1 may go into triode region or M1 will go out of the desired region, and it has to be greater than minus 0.75 volts, otherwise M2 will go into the undesired region. Okay, so you take the worst case limits from all the limits imposed by transistors. Okay, so that's how you calculate it for multiple transistors. Though we have not discussed many circuits of that type, even if you encounter a circuit with multiple transistors, you should be able to use exactly the same procedure. Okay.